Hello and a good day to everyone. My name is Matthias Fuchs. I'm the author of the 4532 class, the Enterprise Memory Forensics in Depth class. Pretty new at Sense. We are just out of the beta and we have the first runs scheduled. And I just wanted to take that opportunity to talk a little bit about how the very historic concepts of memory forensics that we used over many, many years translate to large scale incident response. So, which of the factors that we used in the classical memory forensics do translate into large scale memory forensics? First and foremost, you do need to understand how to do memory forensics on a single machine to translate all of the concepts to enterprise memory forensics. That's super important. Like always in forensics, if you don't understand what you're working with, if you don't understand how your tool works, you will eventually fail. You will get wrong results, you will misinterpret results. So, for that reason, it is super important to understand what you're doing, particularly today where we have very powerful tools that seem to be easy to use. But that slowly trick you into believing you understand what their output is, right? And that might make you miss a few things in investigating attacks. But let's get started right away. So one of the modern tools that we have today is Velociraptor, and I actually have an instance running here locally. But before I dive into that, let's just quickly look into the concepts that we used in the past to do memory forensics. So first of all, it's mostly about detecting malicious code, right? We do have other means where we need memory forensics, so we can investigate the behavior of an attacker in the network, behavior of users in the network, and so on as well. But now this little webcast here just focuses on the technologies that are there to detect malware execution or malicious code execution, to put it correctly. So first of all, in the 508 class, for instance, when we talk about memory forensics, we have a multi-step process to identify malware. And mainly a malware author has two options. So either the malware author runs the code in a separate executable, like it's a separate executable file, or the opportunity that you can also have using the Windows APIs, injecting into some other processes memory and executing from there. But the first steps cover a process running in its own memory space as its own process. So first and foremost, you will have a lot of different tools to display processes in running operating systems. Because one of the main differences when you do enterprise incident response is that you will have to deal with a lot of switched on machines rather than many dead images of switched off machines. So that means we can and have to leverage things that happen in a running system. So when we think about Windows, the easiest way to get a process list, at least for the user, is to open up Task Manager. And that is basically not the worst step to do, especially today. Um, in older Windows systems, up to Windows 7, it was quite easily possible to unlink processes from a so-called doubly linked list. So when the kernel manages processes in Windows, it does so by using so-called e-process structures. And those e-process structures are linked to each other. Every process comes with its own e-process structure, and this one is linked to the next process and to the predecessor of that process, right? And what Task Manager does is it just walks that list, right? So in older Windows versions up to Windows 7, it was possible to unlink a process from that double linked list without too many issues, right? So the process would still execute. The only downside, sort of, was an upside for the attacker. Downside for the defender is that it does not show in Task Manager or any kind of tool that uses the Windows API to iterate the processes, right? So that means for those older operating systems, it would be dangerous to use tools that leverage the Windows API to get a process list because that might not show a few processes. Now that we are mostly dealing with newer machines, hopefully, we don't have that problem that much anymore because unlinking a process from the doubly linked list is actually something that very deeply interacts with the kernel. And operations like that are today protected by something called PatchGuard. So Windows, starting with Windows 8, implemented PatchGuard, which tries to detect manipulations in kernel structures. When it detects a manipulation, it has no way to repair it, but it will just crash the system. It will blue screen the system pretty much. That does not necessarily have to happen immediately after the malicious modification of a kernel structure, but it will eventually happen over time. I've even had cases where it took like an hour before the machine crashed after manipulation, but it will eventually crash and will make the user aware that something strange is going on, because the blue screen will tell you that some strange manipulation was detected, right? So that means whatever technique we apply to the enterprise could be quite useful still, even if it uses the Windows API. Other factors that we were looking for in memory forensics were network artifacts, right? So if you have malware that needs to call back home, like command and control infrastructure, for example, it will need the network. Network objects are also managed by the kernel, so PatchGuard will also protect them. That means the normal means using the Windows API to get the network artifacts will totally do in large scale forensics, right? You still need to understand where certain things are in memory, but this part is covered very well with quite standard tools. Where it gets a little bit more technical and where we need additional tools, that is when it's about code injection. So Windows does not really help you very much with that. So the Windows API allows a process to inject code into another process that is owned by the same user. In other terms, a system process running under system privileges can inject into whatever process it wants, right? So this is interesting because you can basically detect it on different ways. So first and foremost, the network detection works regardless if it's malware that's running in its own process or if it's malware injected into a different process. Because in both situations, the malware will communicate to the command and control server eventually, if it's something like a Trojan or anything like that. The fourth thing we looked at was code injection, right? So someone was injecting code that's supported by the Windows API. You can inject, I already said that. And that can be quite dangerous, right? Because it hides in a legitimate process. Having said that, you might still have ways to find that out. The question is, if it's easy on one machine, is that also something I can run on 10,000 machines all at once? And the good news is today you can. I'll get to that in a moment. When we talk about hooks, so what is a hook? Well, basically, hooks allow external programmers to sort of extend the functionality of Windows. So obviously, certain flows of events in Windows are predetermined by whoever was the coder of the specific module in Windows, but you can interact with it. So for instance, when you write software that wants to interact with your clipboard, and read out data from your clipboard or write data to your clipboard, that is something you can do. Think of your browser. So, for instance, very often today, websites offer you the ability to load things on the website directly into your clipboard, right? And that only works because the third-party browser interacts with some APIs to do so. But you can also hook those APIs to basically catch whenever something is going through there. So whenever someone puts something into the clipboard, you can react to it. A good example would be home banking Trojans. So if you would write a home banking Trojan that wants to, divert funds to your accounts, then that is something you could leverage. You could listen to anything that gets added to the clipboard and see if it's basically the structure of an IBAN, right? Because think of it from a user's perspective. Users often receive invoices, they copy the IBAN out and copy it into their home banking application. So what an attacker could do is they could, for instance, replace that with their own or one IBAN that they control, right? And when the user pastes it again, and it's, well, looking quite similar, like having the same country prefix, for instance, many users won't check any further and will send the money to the wrong account. So that is possible, right, with those hooks. So hook detection can be important, but whatever hook you have in the system, it needs some handling code. And the handling code needs to run somewhere. And that sort of sets us back to the other steps that we already discussed. So you will have some sort of malware or malicious driver loaded in your machine, and you can check that out pretty easily. So let's get back and get rid of that overlay and discuss how Velociraptor supports large-scale memory forensics. So Velociraptor is a currently free and open source tool. You can use it in many different working modes. So the working mode that is interesting for enterprise response is the agent server mode, where you run a central server, you install many agents on machines, and you can control them. It's an all-in-one remote forensics and incident response tool. It's very, very powerful, and it also supports out of the box quite a few capacities when it comes to memory forensics. In the 532 class, we do cover quite a few more, right? Because in Velociraptor, you can build your own content. It's a very extensible tool, and that is something that we leverage in our class as well, right? But let's see what we have out of the box and try to map that what we saw to what we saw before on that little graph. So first of all, Velociraptor works on something that's called artifacts. Let me just refresh that real quick. Oh, now it died on me. That is not very nice. Let's get started again. Sorry for that. Okay, so in Velociraptor, we're talking about so-called artifacts. An artifact is basically an asset defined in YAML that orchestrate things that Velociraptor can do out of the box, right? So it uses some ready-made functionalities, some ready-made plugins to get data out of the system, and then it works on the data. Okay, so when you look at that whole thing, it's quite straightforward. You can see there are like tons of different artifacts, and this is just out of the box, right? There is even a marketplace where you can get more. But let's start at step number one, where we're looking at the specifics of running processes. So for that, we have a ready-made module that's called pslist. I'm just picking the one for Windows now, but you could also have it for Linux and macOS if you want to, because Velociraptor runs on all these three systems. And particularly for Mac, it also supports both infrastructures. So it supports ARM as well as it supports the AMD 64 infrastructure it had before. Okay, so when you look at that, what that does is it basically invokes a plugin called pslist that gives you a list of processes, and it extracts a couple of fields. Now, when you want to judge if a process is legitimate, well, first of all, I'm interested in the full command line. So where does that thing live? What is the executable called? The command line can be a little bit dangerous, so we're going to dive into that in the 532 class. Just as a short teaser here, the reason why a command line is always dangerous is that the storage space, while the general storage space for metadata for a process is kernel level, that particular part, the command line, lives in a so-called process environment block. And the process environment block is in the space, in the memory space of the process. So in other terms, the process itself can modify it. And when the process itself can modify it, obviously you can put in whatever command line you wish, right? And that could be dangerous at times if you only go for that, but you also look for executable, for the full path, who executed a program. So for instance, if you see a notepad running and the notepad was launched by system, that's rather strange, right? Should not happen that much. You also get the PIT and the parent PIT. So that means you got all the data you need to build a process tree. And that allows you to understand who started whom, which is often a very good way to figure out what process could be malicious, right? The second part was network. So there's a whole section on Windows network artifacts. But the one that might give you a little bit a hint about malware running is netstat. So as you can see, netstat also runs, the netstat artifact also runs the process list first, and then it looks for all network structures and it hooks it up to the corresponding processes. The advantage of that is that you know which process is communicating to which to which IP address and port, and when it started. The interesting thing is, as you can see, it uses a built-in plugin rather than the Windows netstat tool. So if someone played around, modified the Windows tools, will not fall for that modification. That's important to understand. You can do a little bit more in here on a network level. You can even set up a PCAP, but that is not related to our few steps that we need to identify malware network. The next part was injected memory, right? So when you inject memory, let me do that. When you inject memory, there are quite a few plugins. So there's one plugin that helps you when you know what you're looking for. So for instance, if we assume that we have Cobalt Strike injected somewhere, then we can just use the Windows detection Yara process, because that allows you to apply Yara rules either to all process memory or to process memory of selected processes. And when you look at that, there's already a predefined Yara rule, and that is, well, coincidentally, the one for Cobalt Strike. But you can put in whatever you want. Just be aware that this will put some strain on the target machine. But when in like older iterations of memory forensics, we were applying Yara to memory images, to dead memory images. We can do that now live, and we can do it on thousands of machines all at once. So that is some huge differentiator. Once we found it, obviously there are additional steps that we learn in memory forensics that are important to deal with the data, right? This will only give you the information that it is there. It will not tell you how it got there. It will not give you the configuration of it, and so on. So you still need to do a lot of things. If you really want to dive deeper down into memory, we can even get the VATs. So VAT are virtual address descriptors, and I sort of describe it usually as the MFT, the master file table of a process, right? So it's very comparable. So when you want to address certain locations in memory, sorry, on the hard drive, you have in an NTFS file system the master file table that tells you where certain files are located, or the data for certain files are located. Plus, the MFT stores some metadata, right? Like permissions indirectly. It stores timestamps and so on. And that is very similar to the VADs, because they also store metadata to a process. Obviously, the metadata for a process is for a process space is slightly differently than the ones for the hard drive, but the VATs are pretty much the file system of virtual process space that we have in here, right? So as you can see, that's a larger artifact, but in a nutshell, you can really iterate the VAT and find outliers there. So for instance, plugins that try to detect injected code, they are looking for mislabeled VATs. So VATs come in different types. So for instance, there is the image type. Obviously, the process image should be executable. You want to execute the process executable. You also want to execute DLLs. They also image type VATs. But if it's not an image type, you don't want to find executable code in there. So a very easy way to identify malware that's been injected is looking for non-image VADs that have execution permissions. That is something that a lot of plugins of memory forensics tools have been using and still use today. So, for instance, memprocfs has the so-called find evil functionality, and in the find evil functionality, it uses methodologies just like that to identify potential malicious code running in the process space of a different code. And now you can do all of that over thousands of machines all at once, and that is pretty neat, right? So before that, that was very strictly on the dead image of a single machine. You could do it partly. You could do it at least with Volatility 2. You could do it on live machines as well if you had the corresponding driver installed, like WinPMem, for instance. Volatility 3 loses that functionality because it cannot work on live images anymore, not even with a corresponding driver. So this is that part. Regarding hooks, there is no direct hooking module in there that gives information about hooks, but that is not necessarily something you need at this point. You could build it yourself if you want to. So that is something we're going to discuss in the 532 class. But out of the box, that functionality is not there. But you can still find malicious code, malicious drivers. So you can go for drivers, for instance, and that might help you to identify hooks in the system. So in a nutshell, we covered all of the different steps that we had in classical memory forensics. And you can see we can translate that to large-scale memory forensics on the network. And this is something that I propagate very much in the 532 class. So obviously, we're going to spend a lot of time to understand how memory works, because that is still important, regardless if you apply memory forensics to 5 machines or 1,000 machines. But we will extend that further. We will extend that further into the enterprise, and you will see how powerful that can be today to find things that you probably haven't found in investigations so far. That goes down even to access data, like credentials for platforms that attackers use to exfiltrate data. So technically, you could even delete the data that attackers exfiltrated if you get lucky. So that is something that you can mostly only get with memory forensics. And you can only get it when you look at all the machines of an enterprise rather than just a few selected ones. So if you got any questions, don't hesitate to ping me. So my Twitter handle is on the screen. Should be on the screen at least. Let me see. Yeah, it's there. So you can always ping me there. Otherwise, I hope to see you soon in the memory class, in the new enterprise memory class. And with that, I wish you a great rest of the day and bye bye.